So if you know your stuff, then you know the differential equation for logistics is Kp L minus P, at least in the form that we use. There's a second form that's also used, but you should be able to go from one to the other. If that, then the population equation for logistic growth is that. In this case, you're being given differential. So right away, you see that K is 3 and L is 10. Yay. So if you put the equation for population with L and A, or L and K in, and it becomes something like 10 over 1 plus A e to the negative 10 3 t. Well, I suppose negative 30t. Wait. All right. To find A is a relative amount that relates how many there are to start with uninfected versus infected. So remember that A is the ratio of the uninfected, which is the total take away the initial population, is the ratio to the initial population. So in this case, L, we said, is 10, so 10 minus 2 over 2 is 8 over 2. A should be 4. The complete equation then is 10 over 1 plus 4 e to the negative 30 t. Did you get that?
Yeah.
Cool. What is the population when the population is going fast? What's the idea there? Half the carrying capacity when the population is half the carrying capacity. In this case, that's half of 10. So when the population is 5. That's also one of the ideas we're involved. So that would be easy, huh? Not too bad? Okay. As I said, the test is Wednesday. I said last week it was going to be Tuesday, but I think Wednesday works better. First of all, just to give you one more day to get logistic on down like that, which is on the test. And also because there's a lot of basketball Wednesday, and if you wanted to go that night, there wouldn't be homework. If we put the test on Wednesday, there wouldn't be homework that night, so you could just go to the basketball game and have fun, right? Or both basketball games. Are you with me?
Yeah.
Okay. Isn't it Wednesday?
Yeah.
Oh, okay. All right. Or you could just sit around watch Netflix, whatever you do with your time. All right. Series. This is an introductory kind of problem, so this shouldn't be very difficult. I hope. So, the idea is series, which you have touched on a little bit before, but first of all, vocabulary. A sequence is what? Yeah, it's a mathematical pattern, a list. Following a pattern. Actually, let's go list following a pattern. Think commas. For our purposes, there should usually be an equation that relates or makes the terms. But it's do. The notation for that is A sub n. So for example, if A sub n is the general rule of negative 1 quantity to the n over n factorial, then what is A sub 3? Or the third term? Negative 1/6, yeah? Because 3 factorial is 3 times 2 times 1, 6. Are we cool? Okay, it's just terms. A series is the sum of a sequence. It's not just making a list of numbers, but adding the numbers in those lists. Now, the notation for that is typically capital S for sum. And it might look something like this. You could use sigma or summation notation. 1, 2. Now, this here, if you end it, then this is a finite sum. This, in expanded notation, I hope you have enough room for this. This is summation notation. Expanded notation would be something like A sub 1 plus A sub 2 plus ... through A sub capital N. This is a finite series. It ends at the capital Nth term. Now, I understand there's a little bit of iffiness in the double N thing. Little n is just keeping track of what number term you're at. So when I say little n of 3, then that means you're on the third term. Capital N is meant to signify the end, or how many terms altogether you're supposed to know. You follow? Okay. We will focus more on infinite series. Now, if you look at an infinite series, you don't typically then write an index. You just let S. And if there's nothing here, it's implied infinite. In summation notation, instead of, I'll give myself enough room. Sorry, I'll give myself a little more room. In summation notation, you still need a counter, but instead of going to a finite number n, you go to infinite many. Okay, so then, and again, as I hit here, an implied infinite. You with me so far? Okay. Now, a series, or the sum of infinitely many terms. Now, that right there feels like it's not possible. How do you add infinitely many things? And yet it's possible, you'll see. A series converges if the sum, as you add more and more terms, approaches a finite limit. Now I'll say that a little more mathy in a second. A series converges if the sum, as you add more and more terms, the sum approaches a finite limit. Have that down? Cool. Okay. Now when you say the sum approaches a finite limit, you're really saying as you add more and more terms to what you already had, that sum starts to approach the top. Now, what you already had is called a partial sum. Take a look at this here formula. Now this is an infinite series, as you can see, first of all, because there's no index saying stop it here, and also because the top is given infinity, all right? If I say find the first 5 partial sums, then let's start by saying what this would be expanded. Wouldn't you say that this is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5? Starting with 1 because that's what they told us to start. Cool? And this is actually one of the most famous series in all of math. It's called the harmonic series. It's really basic. It's just the denominator going up by 1 each. They're all positive. You'll see it's a huge idea. Shortly, 125-ish. Okay. Now, when I say the first 5 partial sums, I mean, if I said just S1, then that implies the sum of the first 1 term, which is 1. S2 is the sum of the first 2 terms, 1 plus a half, or 1 and a half, or 3 halves, or 1.5, whatever you want to call it. Okay. S3 is 1 plus a half plus a third. Now I know I left off with 3 halves, and now I'm adding a third. So adding the previous total of 3 halves to another 1/3, this is going to be a source of a lot of lost points because your fraction skills are a wee bit rusty. The common denominator is 6. 3 halves becomes 9/6. 1/3 becomes 2/6, giving you a total of 11/6. Okay? You say that's kid stuff, but you just wait. See how many people miss these. S4 will be the sum of the first 4 terms. Now I could list them all, but let's just cut to the chase. Wouldn't that be the previous total plus the 4th term, which is 1/4, common denominator being 12. I said 24, but 12 is a lesser common denominator that we could use. And so maybe 22 plus 3, or 25 twelfths. Cool? Alrighty then. What about S5? It did say find the first 5 partial sums. S5 is the previous total 25 twelfths plus the next term in the list. The fifth term is 1/5. Common denominator is probably 60. Yes. So 25 twelfths becomes 125 plus 1/5 becomes 12, giving me 137/60. Okay then. If we are to graph these partial sums, they are growing, obviously, but they're growing at a decreasing rate. So the question then is, are they reaching a top floor, or are they just going to keep growing? Now that's actually a really big, complicated question, and proving it is even more complicated. That's a big idea to come, but for now I can tell you that this does not converge. It grows slowly, but it keeps growing, and it never stops growing. An infinite series converges now if there is a limit to the partial sums. In other words, if as you add infinitely many terms, the partial sum approaches a finite number, then S, the infinite sum, converges. That says converges. Okay? If the limit doesn't exist, which could happen for a couple of reasons, either it just gets infinitely big or it bounces back and forth oscillation, then it does not converge, which is to say it diverges. Would you, just for the sake of practice, get out your calculator, please, and find the 30th partial sum of the harmonic series. For those in the Inspire, find the catalog button next to the 9. Just push the button next to the 9, which is, to me, I think is called the catalog button. I don't know. This button. When you push on that, you should see in the second row, I can't remember, there's a summation notation. Is that true? Is it second row? Okay, second row, go over and call that up. And then basically just type in what you got. Now those of you with an Inspire, you're going to math 0. What do you got? Math 0. Yep. Math 0. 84 people. Type in everything you got. N equals 1 to 1 divided by n. 230. Whoa, man. That's a big fraction.
It's 4.
It is not 4, I assure you.
3.987.
Yeah. It is approximately 4. Okay? Blah, 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 blah. Just about 4. How about that? That's it. It does not equal 4. And if you were to add 100 terms, it would blow past 4 eventually and keep going forever. I don't know, maybe 100, but if you added enough terms, it would go past 4. In fact, it never reaches an upper limit. Although what you're adding, see, there's this great calculus play, which is one of my favorite ideas of calculus. There's the play between what you're adding is getting infinitely small, but you're still adding infinitely many. And on an integral, that often converges. So you get a number. But on a series, sometimes it converges, sometimes it does not. All right, now, for now, the main thing I want you to understand and get into your brain is to read carefully. I can't tell you how many people mistake sequence versus series because they don't slow down and think the difference between the two, all right? The sequence is the terms, the series is the sum of the terms. So if I gave you this here series, infinite series, and I said the harmonic, then I could say, for example, I might ask you, what's a sub 30? And that is 1/30. I could ask you s sub 30, which is the sum of the first 30 terms, what we got above, right? Now, in terms of graph, we don't graph series nearly as much as we graph functions. We just don't, partly because they're not continuous. But if I were to graph the sum of the terms, then they would be dots, not continuous curve. And the first term is 1, the next term is 1/2, the third term is 1/3. And as I go on, the terms would approach 0. Yeah? The sum, didn't gauge my space very well here. If I were to do partial sums, the sum of the first 1 terms was 1. The sum of the first 2 terms was 1.5. The sum of the first 3 terms was, can't remember what, 11.6. Okay, 2, just shy of 2. The sum of the first 4 terms is 25/12. So now it's a little above 2. Now you'll see that although these tend to grow slower and slower, there is no, if I couldn't draw an asymptote fencing and all, they don't ever reach an upper floor. The rate of change here between any 2 points is automatically linked to the next term you're adding. Each time it's changing by the next term. And you know those are going to 0. But they never get there. All right. This then, on first glance, feels like, okay, maybe it reaches an upper limit, but maybe not. We'll come back to that in a second. What about S of n, or this infinite sum of n squared? What is the sum of terms going to look like? 1, 4, 9, okay? So even more powerful then is the sum, the partial sum. First, sum of the first 1 terms. 1. Sum of the first 2 terms. 5. Sum of the first 3 terms. 13, and so on. So you can see then that this definitely diverges. Up here you might put might converge, because at least it looks like it's growing slower and slower. This one definitely diverges. All right? Now that then is because the terms are getting big. If you're adding infinitely many things, and the terms are getting bigger and bigger, then is there going to be a sum? It's got 0 chance. If the terms get bigger and you're adding infinitely many of them, it will diverge, period. There's no chance for it to converge. All right? If the terms get smaller and smaller, then it might converge. But we'll get back to that later. What about cosine of pi n? If I were to graph the terms, the first term is when n equals 1, cosine of pi is -1. Second term is cosine of 2 pi, which is positive. Third term is -1. Fourth term is positive 1. So if I were to look at the partial sums, the first partial sum is the sum of the first term, which is just -1. The second partial sum is the first 2 terms, -1 plus positive 1, which is 0. The third partial sum is -1 plus positive 1 plus -1, which is -1. Well, then, it's going to bounce back and forth between -1 and 0. And so would you say that this sum converges or definitely diverges? It definitely diverges because, again, this limit, there's no finite limit. It's not approaching a number. It's constantly back and forth. What about ye owed 1/2 to the n? What kind of series is that? That's okay that you don't know it. We'll cover it in set 117. That's the geometric series, or a geometric series. A sub n. at the first partial, or at the first term. What is the first term? 1/2. What's the second term? 1/2 to the second, or 1/4. Third term, 1/2 to the third, 1/8. Fourth term, 1/2 to the fourth, 16. Cool. Now if I were to add these, or track the partial sums, the sum of the first one term, 1/2. The sum of the first two terms, 1/2 plus 1/4, 3/4. The sum of the first three terms, 3/4 plus 1/8. 3/4 plus 1/8. 6/8 plus 1/8. 7/8. Okay? First four terms, 7/8 plus 1/16. 15/16. Five terms, 15/16 plus 1/32. 31/32. So, you start to see it approaching a limit of 1. This converges to 1. Geometric series will converge if the common ratio is between -1 and 1. All right. Now all that said then is just a starting point for later. Are you with me so far? Sequence is a list. Series is a sum of the list. I didn't do this last year, and I kind of regret it. So I'm trying to get this idea in a little early. All right? There's a little bit of funkiness to be had here, because not only do you deal with numerical series, these are all numerical, because once n goes in, you've got numbers here. But sometimes you deal with functions defined as a series here. These are called power series. And they are pretty stinking amazing, okay? By the end of the year, you could tell me what sine of 2 is without a calculator, accurate to 8 decimals. Just like that. Okay? Yes, with a power series. Okay? So, towards that end, let's start that. Say I gave you this here power series. Now this is defined, or a power series, or a polynomial defined function. And what it's looking at is a sum of stuff from 1 to 1. Now I'm taking it easy. In other words, the question is where does the 1 go? Does it go in for the x or the n? And it goes in for the n. There you go. That's expanded form. Done. Okay? Now, if you went instead that same function, but from 1 to 2, then p of x, which would be the second degree Taylor if you went on, but would be first when n equals 1 goes in, I get x to the 1. The sum means to add, and then I go up to when n equals 2. And when n equals 2 goes in, I get x to the second. Okay? So what do you reckon the third one is? X plus x squared plus x cubed. Okay. If you were to sketch this, obviously x to the first would look like that. x1 plus x2. No, it's, or x plus x2, or x squared. What am I, sorry, that's called square. That's x times x plus 1, right? So maybe something like 0 is at 0, -1 in a parabola. Okay? X plus x squared plus x cubed. Let's just focus around the origin. It will definitely go through 0. At x equal 1, it would be, or is, 3. At x equal 2, I could like factor this out. 1 plus x squared. Doesn't really do much after that. At x equal, what about at x equal -1? I agree, -1. Okay. So it'd be something like this, and it would hold up for a little bit. The cube would eventually win, something like that. We could take the derivative and find one, but that's not that important. All right. My point, though, is if you let this go to infinity, you'll see that this starts to approach this. Which is kind of like 1 over x minus 1. Now you might think, so what? I mean, that's so what, right? Because 1 over x minus 1 isn't that hard to deal with anyway. Why use a series? Well, with that, you could do arctangent and all this great stuff. Log. Oh, so. You'll see. You'll see. Hold on there. What if I said p of 2 for the first one? What's p of 2? Now that then goes to, where does the 2 go? P was a function of x, and so if you say p of 2, then you're saying x of 2. So for this one, p of 2 would just be 2 to the first, or 2. For this one, the power series would be p at 2, which this time would be 2 to the first plus 2 squared, or 6. Okay? The third degree, of 2, is 2 plus 2 squared plus 2 cubed, or boom. Now would you go back and change? These should have been indexed this way. First degree, second degree, third degree. That represents the degree. Oh. All right. You try. Try the one below it. 1, P1, P2, P3. Yeah. Oh, no.
Yeah.
Oh, yeah, no. You silly. Not sillies. I guess you don't know that. 0 factorial. It would be logical to assume that's 0, but in fact it is 1. Yes, it is 1. 0 factorial is 1. We'll prove that later. For now, I guess just take my word for it. But yeah, 0 factorial is 1. Crazy mathematicians. Oops, this is yeah, I'll leave it like that. You can leave the factorials, or you can simplify them, whichever you prefer. Okay, cool. Now then, yes?
On the first one, don't you have to add x to the first?
Oh, plus I didn't go out to x to the first today. You're right. Sorry. Good point. Okay. Sorry, you're right. Thank you. If I were to sketch these just roughly, this is cool. 1 plus x looks like this, obviously. 1 plus x squared looks like this. 1 plus x squared plus x cubed looks like this. If you were to go to the fourth, it would look like this. And to the fifth, it would look like this. And what does it look like it's approaching if you cover up this? Come what does that look like, my friends? This is e to the x. That, gone to infinity, is e to the x. Now, all that again is to come. My point then is, if you let this be a function of any old x, then it will model or can model a lot of really ugly functions like e's and logs and sines and cosines that work for any old x also. That is called a power series. It's a series of terms to a power, polynomial terms that are easier to deal with than e's and sines and cosines. To be continued. All right, that's it. Questions on the fun sheet? How did you actually had all day the other day, so it's pretty much done, right? Am I done? I intended to put the key up, but then I figured, copy fest, so I didn't. That and I forgot. I just kind of just forgot. So, I will put the key back up here on the old front table and let me know if you have questions. You still have 15 minutes left. If you know you have questions, let me know and I'll be happy to help you. So, Timmy.
You explained this kind of at the end of the class. The virus problems were experiencing.
Okay.
Can we just... Oh wait, hold on. I struggled through this.
You're starting place.
Oh, DMV? Okay.
Yeah.
Oh, wait, I
Now
know
what?
this one.
Population.
Number one.
That's a starting point, right?
Yes, so that's...
That's L. That's the carrying capacity, that's the closest view.
Okay.
All right, so here's the yesterday, and then today. In terms of establishing a time frame, the earliest possible time we have is this. So it seems like yesterday is 0. The population was
Oh, I did one. I plugged in and it was no, it was one. I did like 1 minus 1.
that. Started on a population expression for
So you have the L, oh, so you're trying to find K.
You will have to find K. If you have everything, if you know L, you have everything you need to and you need a second phase. So plug in L in.
Yeah, because like if you find it, because it's just asking finding out the two, and then you're going to tell them to like whatever the other value is.
What? In that case, it's like 14, oh, yeah, see. I'll be happy to answer questions. It's not easy. And my key might not necessarily make it fully clear. Or if you'd like to do questions at the board, I don't know, I can do that.
Maybe 14.
14, sure. B on the board.
Wait, could you just explain it, like, because we got that it just wasn't there at 6. So why would it?
Because 8 is actually,
I don't know why we're leaving that, but it's just, like, I just had that.
so that's actually a good question.
Maybe
I can say this. Let me go biology versus math.
Yeah,
Okay.
Oh, that's 0.5. How do you find that's
The monthly equation, why do
So it's like a
Uh,
times equals.
6 minus 3, is that what that was? 6 minus 1? Okay. Now, in true life, real biology situations, something can actually reach the carrying capacity. You can say the field can take 50 volts, you can hit 50 volts. In math, however, the equation that we use to model okay, consider why the population and the way we have it set up really can't be L. The only way for the population to be L is if this was nothing. Do you agree? You see what I'm saying? Well, that really can't be nothing, because each anything is never zero, and A, assuming it didn't start at nothing, has got to be something. So the model, the math part of it doesn't necessarily hit the biology super well, because in real biology it can equal the carrying capacity, but our equation can't. Now that said, this equation, I'm saying that the range is what it is, because in terms of, remember, range is y low to y high. And so first thing is don't fall into the trap that I did, going left to right. Mine actually read 8 to 6, because left to right, that 8 came first, you know what I mean? Well, that's stupid, because you don't go higher. So that's, I didn't even catch that was erroneous. The low y is 6, the high y is 8. Now let's talk about whether it's an include or not. They say at time 0, that's on the line. It is included. But in terms of the carrying capacity, mathematically, you never hit a y, you can't. It's a limiting approach, but not a quality. And so it is not.
So just because that's the only thing they actually gave you, you can't.
Okay, so now this is the second thing. So this problem got a lot of people, not because they didn't understand it, just as they did, but because they did. I thought the question was bad and that they did so much running around between things. So first of all, understand that this differential equation, 8, what is it? Y over 8, 6 minus y. This could be any billion number of equations. That's why we do a slope field, depending on, this is just a rate of change, and remember, rates of change could be a million different things, right? Remember back to that. So when I get that differential equation, it's an infinite number of possible curves, or even decays, and I don't even know. In this problem, they give you 2 specific cases. They give you, hey, there's one case called F, and F has the point 0.08. And so when they say, what's the range of F, they are not talking all these possible curves, they're talking this curve only, period, okay? And that was the gotcha, right? Okay, only that one. Then later on, I think I said G, throwing G that went through 3, 2. So that's the one that only goes through 3, 2. This is G. And so remember, there's this play between lots of possibilities and any definite ones they give you. Okay? I round to the nearest people, but in the AP test they will say. That's fine. I didn't say. Let me know if I can help. If there's anything else. So you are going to separate the variables and integrate all of that?
No, I was gonna say, why is like my points, like these are the points, and then,
Oh, it's
So that means, but that would give you that.
Because it's half of L, L is
You'd be using that to find a tangent. That would be the question to find a tangent.
Wait, I just looked like I crossed out. Okay, thank you.
Oh, this is what I was talking about earlier. So for that math competition.
Oh, yeah.
So like I read that problem for the last one. For this one, because remember I thought it was
Oh,
like
yeah,
the sum of like 1 plus 2 plus the last term squared. So I made this, which is what that is.
Oh.
But it's still cool. So like when you plug in all these things, it's like this, and it goes upwards. Yeah, but then so like this is how much the difference between them, and then between everyone it's 3. So is that like how does the like derivative relate to that? How does
So this would imply that the original series is quadratic.
negative 30.
Because the rate of change is negative. And then the change in the change. I would take
So we're going down, so we're going down.
which is actually.
Yeah. So how do you write so I can write assumptions for that, right? Because I'm just trying to write them.
No, I think.
Yeah.
That makes sense.
You could use something like this.
Alright, noted.
So,
Oh.
So verify that works 3 and goes 4. We call this 1. That is 2.
Oh, that's okay. Wow, that's
Yeah, isn't it?
it's like it was almost kind of what we were talking about with the power series, but now
Yeah.
like because it's not really.
Literally like 4 points
Like for like any like well if you write any sort of thing you could find like a pattern in there.
Saturday is sometimes hard to see. If I get
Could be like
an E, it does an E, but the patterns would also be E.
Yeah. There's some really one that just got me so annoyed. Like there's this one. It seemed easy to me at first, 4, because
I was like, that looks clearly like 29 volts, not 30.
so there's so many factors, it's ridiculous. Once you start, like I was spending like half an hour on that. Once you start thinking about like all the powers of 10 and everything, so I figured like, oh, this will be easy because I can know how many are perfect squares because it's like basically almost all the factors of it are, but then like powers of 10.
Well, so this is like, this is 2, 6, 5, and 6. And then this is 2 squared, 2 squared.
Yeah.
So basically, it's all the combinations of
That aren't. Yeah. So the first approach I did was like find how many are perfect squares and subtract, but I didn't know how to find the number of factors. Like, I don't know how to do the combination.
So you can do.
If you start doing it, like you realize there's like hundreds. They're like for IBM, I'm sure there's. I'm almost positive there's over like 200 factors. Because it's ridiculous.
Oh my god.
Because you could do, for example, for just like, if you start with a base factor of 3, you could do 3 and 2, 3 and 2 twos, 3 and 3 twos, 3 and 4 twos, you know, and then do the same for 5s, and then do the same for like 3 and 2 and 5, 3 and 2 and 2 5s, 3 and 2, and then, so there's so many right there, and then you take into consideration the powers of 10 and stuff, like, it's great. Yeah. And then this one is crazy. I don't know how you find the distance between C and D or A and B or right. So since this was Camden, it was a right triangle. And then yeah, so I started looking like I saw some triangles. But then I couldn't get it down. Yeah, so the radius one, that's all they get.
I don't know. Oh, yeah, there are actually two questions.
I get that, but you like distribute.
No, this is.
Why not do this?
This is. Oh, I see. So that's the first question. How many countries? Well, you could go with I was thinking reaction. So you go, look to the, I guess you could also say. No, just, I just said. Well, that. This is your fault?
This is important business.
I don't care what Jack says, get off your phone. Have a nice day, make sure I get this by the end of the day. I'll get it back to you tomorrow so you can study from it. Many of those will not be as, the test will not be as difficult as that question. Buenos dias.
Mr. Rickman, I hope you increase your coffee intake because I just got a 10-pound bag of coffee.
What? I didn't know they made a 10-pound bag.
Well, that's what we use when we brew it at the store.
Oh, really?
Yeah, it's the Christmas blend, so we can't sell it anymore, but...
Sweet. I'll take it. Heck yeah.
Great.
That's delicious. Thank you.
Oh, great.
That blend is wonderful.
I'm so glad because my house cannot make coffee.
Thanks. Delete. Delete. Oh, no. Undo. And he was doing like 70 in that back area.
You can get up there if you know where to go.
Yeah.
Should be careful with it.
My brothers, oh, they're so stupid. They pushed my mom over the edge because they just like they kept like doing shit they weren't supposed to do, and now I'm paying for it. And I had such a perfect balance system in place.